This is Nathan Cruz with Carlson Software, and in this demonstration I'm going to show working with Iowa State LIDAR to size a culvert pipe. So the first thing I'm going to do is I'm going to change my scenario projection to Iowa South, U.S. survey feet. I'm then going to load a point cloud, which I've already found and downloaded, which the government site says that it's in UTM zone 15 in meters, but we're going to convert that into our local working system, which is Iowa South U.S. survey feet. I'm going to remove outliers during the load. We can see we're going to load about 4.5 million points, and I'm just going to hit load. Now this particular LIDAR data set does not have any classified data, so you can see that there's no classification that's been done to the data. So we're going to have to run a bare earth algorithm to eliminate the trees and the houses in this particular area. And I happen to know that the area of interest is down through this ravine and through this sort of high spot. So what I'm going to do is I'm just going to crop out the area that I want to use just by following. I'm just going to come along the top of the ridge in this case, so I can pick up all of the water. And even in this mode I can change this to contour and elevation and set that maybe to 10-foot contours. And that way you can see the contours, and it makes it a lot easier to follow the ridge lines directly from the point cloud. So I'm just going to come on down through here, straight across here, right up the top of this ridge, and hit C to close. Now what I'm going to do is crop the point cloud by polyline. So I'm going to click on the point cloud, right mouse crossing, select that polyline, and I'm going to hit crop points. I'm going to put it back in elevation grayscale mode. And you can see we've got a few house roofs and whatnot in here. So we're going to start with the bare earth algorithm. We're going to do a 5-foot window with a maximum of 2 feet, and that'll help pull out all of our trees and smaller vegetation. Then what I'm going to do is up that to a 10-foot window, which is just a wider window. And you can see the more and more trees coming out of here at the 10 and 2. And then I think I'm going to do a 15 and 2. That removes even more points. I can see that there's just a few little areas in here that are left, but I also know that there's a field in this area, which creates a lot of bumps. So what I'm going to do is I'm going to set a 3-foot window and a maximum of 1 foot, and I'm going to apply this filter. And what that does is that'll go through in here, and that'll remove a lot of the corn rows, and there's a little bit of noise in the cloud down in here. And so now what I'm going to do is I'm just going to manually clean up a few of these leftover points that I can see here. So I can see these, just a few floaters in this area. So what I'm going to do is come in and I'm going to rotate up, and I'm going to just draw 4 points around. I'm going to keep enclosed in selection. I'm going to use my point isolator command. I'm going to draw a rectangle around the points that I can see, and I'm going to say keep enclosed, and I'm going to delete those. And I think there was a couple more right in here. So this point selector tool allows you to have a lot more fine-tuned control. So again, I'm going to keep the enclosed in the selection, and I'm going to go ahead and delete those. And I'm going to come back over here. Now these roofs and stuff don't really, they're not really going to affect the calculation very much. But I'm going to put it in a view mode where I can see the majority of the roofs. So I'm going to use the point isolator again, and I'm going to carefully trace a polygon around these points. I'm going to say keep enclosed, and it looks pretty good, and I'm going to delete those. So it looks like we've taken out the roofs, the houses, pretty quickly. Now what I'm going to do is go ahead and create a surface that looks like one more anomaly. Turn off the... But that, with a little single point like that, that'd be easy enough to clean up with the surface tool once we create the surface. So let's go in here. Looks like I did not pick up that particular roof line, so I'm going to come in and do the point isolator again. I do see what appears to be some rogue points way out over here. I'm going to pick those up as well and delete them. And now I'm going to run the one more remove outlier filter. And that just eliminates that much more noise that's left over after you're editing. And I'm going to go ahead and create a surface so I can see 255,000 points. And what I'm going to do is do a grid smoothing of 10 by 10. Because again, this is LIDAR, and I know that there's a lot of noise from vegetation and crop rows. Now I can turn off the point cloud. And we can see our road and other areas. I'm going to go ahead and turn off my polyline here. Now I'm going to use the Google Maps image downloader, and I'm going to tell it to drape, so we automatically know where you are if you set your projection and you load data. So we know where the lat longs are. And I'm going to tell it to drape the Google image, and I'm going to load the hybrid, which has road names and so forth. And I'm going to have it drape it to the surface just so I get a better idea of what the ground cover looks like. So if it's highly vegetated or if it's rocky, or in this case, it looks pretty, looks like a lot of dirt and mixed crops. So I'm going to turn off the Google Map overlay, turn my textures back on, and instead of this being an ashy sandstone texture, what I'm going to do is I'm going to select a grass texture with a lower runoff coefficient of 0.4 in this case, which is my own estimation between the dirt and the grass cover here. It's going to absorb a lot more water. So I'm going to really reduce that so it's more realistic. And that's going to apply it to the entire surface. Now I could also trace out a polyline area and then drag and drop different materials. So if I wanted to average in the asphalt, for example, and draw the asphalt area here and close. I'll turn my polyline group on so you can actually see the polyline. So what I'm doing here is I'm just estimating the road, the pavement in the road, if I want to take that into account into my calculation. If there was other improved areas, could do the same thing. And then basically all I'm going to do is go back to my materials. I'm going to go to paving, asphalt, and I'm going to drag and drop that inside that polyline. And then I'm going to turn my polylines back off. And now what I'm going to do is go and check my storm settings. So I'm going to calculate a storm event so we can get a watershed. And we're just going to we're going to ignore subbasins that are on the edge and drain off the surface, because our area of interest is right in here. Again, if I turn on the Google overlay, you can pretty clearly see where that draw is. So I'm going to go ahead and calculate this storm. And so based on the current big bowl, it looks like that we're inside of one large bowl in this particular case. But you can see where the ponding is that we're going to need to drain. So this is a 25-year storm. I can also download the NOAA rainfall area for this particular area. So I can click on the NOAA rainfall for Iowa, and this will go out to the NOAA website, and download the actual rainfall data and import it in, and it'll apply it to this to the storm. So the next time we recalculate, it'll use the actual rainfall area for this particular region in Iowa. So what I'm going to do now is draw in a culvert. And I'm just going to take it from, I think maybe this, let's see, on the low points here, we've got 675. So I think we're going to pull it right from here and just bring it right straight across the road to this other low point. And now what I'm going to do is, you notice that it's in the same subcatchment area. So what I'm going to do is I'm going to turn on the create subarea inlet at the inlet pipe, and I'm going to recalculate the storm, which is also going to apply that new NOAA rainfall library that we just downloaded. Now during this calculation, it's going to use the runoff coefficients for the different texture areas inside of each subcatchment basin and calculate the average runoff coefficient, which is weighed. So in this case, basically now we have a subcatchment basin up in here for this particular culvert pipe. And if you look at the surface carefully, you can see there's actually kind of a high spot in here. And if you know that that's not the case, then you can manipulate the surface and do a little bit more cleanup. So if you know differently, or if that really is a low spot ponding area here and a separate ponding area here, which you can see in a little better detail, then basically we could just do two culverts across the road, but it'd be probably more cost efficient if this channel was pretty much dug out and this pipe started from here. So how can we connect these two? And we'll do a quick surface edit. And all I'm going to do is I'm going to add a break line, and I'm going to turn on my node snap, and I'm going to tell it to go from this node to this node and press enter. and that's going to create a lower point. Let's see, let's try another. Maybe go straight across here. And then what I'm going to do is take this particular point and I'm going to lower it. Just right click it after I select it, I right click on the mouse and I'm going to lower that. And I'm also going to lower this one. So basically we've just created an artificial channel in between here, so we can see that by turning on our runoff tool, and we could see that it's now draining. Probably got it a little bit low in here, but we've definitely connected these points, so we've created an artificial low point in that case. So I can take and re-edit the surface, and what I can do is I can set the elevation of this point based on the slope between two other points. So what I'm going to do is set point elevation by slope, and I'm going to click on this elevation and this elevation. And what that just did was it just flattened out that path, so we don't create a super deep artificial pond. And now that I've modified the surface and cleaned that up a little bit, I'm just going to hit calculate again. And that should effectively join these two areas together, because if you look at this entire area, it's just a one giant bowl, and this happens to be the low spot down in this ravine. This is still pretty shallow in this particular area. So one thing that we can also do is we could extend the pipe a little bit further, but more than likely we probably wouldn't want to do that. But in this case, we're just trying to get an estimate of the culvert size. So in this case, we have an 18-inch culvert, and we've got a peak flow of only about 6 CFS or so for this particular area. And you notice that the average runoff coefficient reported up here is not just 0.4 like it is out here. Here it's 0.041 because this paving is a 0.65 runoff coefficient. So you get this average weighted runoff value. The other thing that you could do, depending on these elevations, 675 down to 675, is if you wanted to incorporate the entire area, what we could do is we could force a deeper trench between these two in order to join them. But we also have some very simple watershed commands that allow you to combine two adjacent subbasins. So I'm just going to click on that command, and I'm going to combine this subbasin with this one just by clicking on the inside. You notice that we've just now combined those two sub areas. And now what I'm going to do is recalculate the storm. So this is going to force this pipe to go from an 18-inch carrying just a very little bit of water that it found just in this little basin area here. Now we're going to force it. And not surprisingly, we end up with a really large pipe because now we've got a very large area. So we've got 38.24. And so it's probably due to a low headwater result. So what I'm going to do is increase the headwater depth to 5 feet. And now we're down to a 30-inch pipe. And the reason for the 5 foot is if I tooltip over here, we get 675. And if I look along the edge of my road here, I'm getting about almost 682. So that definitely gives me about 5 foot of headwater depth in here. And now that we've got our culvert pipe isolated across the road, and we've calculated its size as a 30-inch culvert that would handle all the water flow, what we can do is we can view that back in the context of the Google Maps surface, and we can see that we're right in those, right in the center of those ravines, even as we're doing this. So when you're trying to show this to a client or customer, they can get a better idea of just exactly where everything is. The Google Maps basically gives you really nice context for your conceptual plan. Now the next thing that we could do is we could calculate the station and the skew angle for this particular pipe crossing. In this case, I don't have the actual geometry, so I'm just going to draw a polyline down the center of Tulip Avenue. And we'll simulate this curve. We'll zoom back in here. Now for any, let's bring that over just a little bit. Looks like we have a little bit of a curve going on there. There we go. Now for any polyline in the scene, you can set the starting station. And so in this case, I really don't know what it is, but I'm sure if it was my project, I would know it might be something like 175028, perhaps. Well, just for example, I'll just put in 1500. And now what I can do is I can select the culvert pipe, and I can associate it with that polyline that I just drew, polyline 4. And now it's automatically calculated the station offset and also the skew angle, which is really steep in this case. And if the maximum skew angle, if it needs to be even, then we could just type in 60 here, and it'll rotate. Now, in that case, we rotated around the inlet, and we didn't want to do that. So basically, we want to rotate around the crossing station and do a minus 60. And now we have an even 60, and we also have the inlet station. So if we wanted to round these to 43, this is going to be slightly different. This would be 2697. And then we still are holding our outlet crossing, so we would call that minus 51. So in this way, you could modify and round up the station values, but that's how you calculate the station offset values for the inlet, the outlet, and also report the crossing station and the skew angle, which is the angle at which it crosses the center line.